Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square ABCD, and one side of square ABCD equals to 8 units. Inside this square we have two circles. The radius of this big circle equals to 2r, and the radius of this small circle equals to r, and we want to find out the value of r, the radius of the small circle, or the size of the radius of the small circle. So before I will start to answer on the question, I will present to you two new rules. The first rule, or rule number 1, is that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. I will repeat on rule number 1 again. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? Rule number 1 states that if, for example, you have this circle, and we know that the center of this circle is at this point that is defined as point O, and we also have tangent to this circle actually tangent AB is tangent to this circle at point M. Actually point M is the point of tangency, and if we have a radius of this circle that is drawn to this point of tangency, that is to say, actually this radius OM is drawn to the point of tangency. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So whenever you have a radius that is drawn to the point of tangency, like in this drawing, this radius OM of this circle is drawn to the point of tangency. That is to say, it is drawn to point M. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, so actually that is the meaning of rule number 1. A tangent to a circle, this tangent AB is perpendicular to the radius drawn to its point of tangency. So this radius is drawn to the point of tendency, that is to say point M, Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees and this angle is also equal to 90 degrees. Okay, actually, that is rule number 1. And we also have rule number 2. Actually, rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I will read rule number 2 again. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? Actually, if we have a circle and this point P, is actually an external point of this circle. Why point P is an external point of this circle? Because of the fact that point P is not located inside this circle nor on this circle, but it is located outside this circle. That is, therefore, it is defined as external point of this circle. So if from the external point P we will draw two tangents to this circle, so this will be the first tangent to this circle. We will define the touching point between the tangent to the circle as point A. This point is point A, and we will draw also the second tangent to this circle. So this will be the second tangent to this circle. We will define the touching point between this tangent and the circle as point B. So as you can see from the picture, the length of the first tangent is PA and the length of the second tangent is PB. And according to rule number 2, whenever you draw from external points of a circle two tangents to this circle, to a circle, then the lengths of those two tangents will be equal to each other. That is to say, PA will be equal to PB. Okay? I'll repeat again. If from one external point, that is to say from point P, that is the external point, two tangents are drawn to a circle, if from this point, point P, we will draw two tangents to this circle, this is the first tangent, PA is the first tangent, and PB is the second tangent, then they have equal lengths. So the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. As you can see, PA is the length of the first tangent and PB is the length of the second tangent, and according to rule number 2, the lengths of those two tangents are equal to each other, that is to say PA equals to PB. Okay? So in the next step, we will define the center of this small circle as point P, and we will define the center of this big circle as point Q, and we will define the touching point between tangent BC to the small circle as point E. Actually, point E is the point of tangency of tangent BC with this circle, with this small circle. And we have the radius PE that is drawn to the point of tangency, that is to say it is drawn to point E. Therefore, the tangent BC is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. And the same thing is true here. We will define the touching point between tangent DA and the big circle as point O. Actually, point O is the point of tangency, or it is the point where tangent DA is tangent to this big circle. That is to say, it is the point of tangency, and we have radius QO that is drawn to this point of tangency, that is to say point O. Therefore, the tangent DA is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? We will join points P and A together by a straight line. We will define the touching point between tangent AB and this small circle as point M. Then we will join together points P and M by a straight line. Actually, line segment PM is the radius of this small circle. Why line tangent PM is the radius of this small circle? Because of the fact that line segment PM starts from the center of this small circle, that is to say point P, and ends at point M, that is a point on this small circle itself. Therefore, line segment PM is the radius of this small circle, that is to say it equals to R. And actually, the touching point between tangent AB and the circle is point M, and point M is defined as the point of tangency, and we have radius PM that is drawn to the point of tangency, that is to say point M. Therefore, the tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, and we also know that all the angles inside the square are right angles. Therefore, this angle ABC equals to 90 degrees. And we will focus on quadrilateral PEMB. on quadrilateral PEMB, we have three right angles, 1, 2, and 3, and the sum of the three right angles is 90 degrees times 3 is 270 degrees. We will define angle MPE, this angle is angle Z. So actually we have a rule that the sum of the angles in any quadrilateral equals to 360 degrees. That is to say, the sum of the three angles in quadrilateral PMEB that equals to 270 degrees plus the size of the fourth angle must be equal to 360 degrees according to the rule that I mentioned. Here we will subtract from this equality 270 degrees and we will get that the size of angle Z is actually 360 degrees minus 270 degrees is 90 degrees. So we found out that angle Z is a right angle, it equals to 90 degrees. So we write here that angle Z equals to 90 degrees in the drawing. So as you can see from the drawing, quadrilateral PEMB has four right angles. Quadrilateral PEMB has four right angles, and we have a rule that any quadrilateral that has four right angles must be at least a rectangle, if not a square, it must be at least a rectangle. Okay? So quadrilateral PEMB is at least a rectangle, if not a square, because of the fact that it has four right angles. So quadrilateral PEMB is a rectangle, and we know that the opposite sides of any rectangle are equal to each other. That is to say, PE equals to MB. PE equals to MB according to the rule that the opposite sides of a rectangle are equal to each other. Okay? But we know that PE equals to R. It is given us that PE equals to R. Okay? We also found out that PE equals to R. So from this equality we will get that MB also equals to R. MB equals to R. Likewise, we also know that PM equals to EB because PM is the opposite side of EB in quadrilateral PEMB. Therefore, PM equals to EB. PM equals to EB, but we have already found out that PM equals to the radius of this small circle, it equals to R. And from this equality, we will conclude that EB also equals to R. EB equals to R. EB equals to R. So actually we found out that quadrilateral PEMB not only has four right angles, but it is also have four equal sides. All of its sides are equal to each other, they are equal to R. Therefore, quadrilateral PEMB is a square. Okay? But if the opposite sides of a rectangle are equal to each other, let alone that the opposite sides of a square are equal to each other. Okay? So what we did here is also true for a square and not only for rectangle. If it is true for a square, let alone that it is true if it is true for a rectangle, let alone that it is true for a square, that the opposite sides are equal to each other in a square. Okay. In the next step, we will find out the size of line segment AM. We know that AB equals to 8 units. AB equals to 8 units. And MB equals to R. So actually MB minus AB, that is 8 units, minus MB, that is R, equals to AM. Again, AB, that is 8 units, minus MB, equals to AE. Okay, I will write it here that AM line segment AM equals to AB minus MB, AB minus MB, line segment AM equals to AB minus MB, but we know that AB equals to 8 units and MB equals to R, therefore AM equals to 8 minus R. So in the next step we will define this point as point G, and we will define the touching point between tangent AD to this small circle as point S. Then we will join together points S and P by a straight line. Actually, point S is the point of tendency of tangent AG with this small circle, and we know that SP is the radius of this small circle because of the fact that line segment SP starts from the center of this circle, that is to say from point P, and ends at point S, that is a point on the circle itself. Therefore PS is the radius of this small circle, that is to say it equals to R, and we have the radius R it is actually drawn to the point of tangency, that is to say point S. Therefore the tangent AG is perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the next step we will prove that those two right triangles can congruent to each other. So we will focus on the right triangle APM, and the right triangle APS, this right triangle. I will repeat again. We will prove that the right triangle APM is congruent to the right triangle APS. Okay, first of all, we know that side AM equals to side AS according to rule number 2. AM equals to AS according to rule number 2. AM equals to AS according to rule number 2. So actually we have here the external point A. It is external point of this circle, of this small circle, and from point A we have two tangents to this small circle, tangent AM and tangent AS, and according to rule number 2, if from an external point of a circle you draw two tangents to that circle, then the length of those two tangents will be equal to each other. That is to say, the length of the first tangent, that is actually AM, will be equal to the length of the second tangent, that is AS. That is to say, AM equals to AS according to rule number 2. And we also know that PM equals to PS equals to the radius of this small circle. PM equals to PS equals to the radius of the small circle. PM equals to PS equals to the radius of the small circle. And we also have here side PA, that is a common side, it belongs to both triangles. So we write down that PA equals to PA as a common side that belongs to both triangles. So we actually proved that three sides of the right triangle APM, 1, 2, 3, are correspondingly equal to the three sides of the right triangle APS, 1, 2, 3. Okay, therefore we actually proved that triangle APM is congruent to triangle APS according to side rule. So I'll write it down. We proved actually that the right triangle APM is congruent. This is the sign of congruent to the right triangle APS according to side rule. So what is side rule? Side rule is that if you prove that three sides of one triangle are corresponding equal to three sides of another triangle, then you actually proved that those two triangles congruent to each other according to side rule. And from the fact that those two right triangles congruent to each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles congruent to each other, therefore those two corresponding angles will be equal to each other. That is to say, angle PAM is equal to angle PAS, this angle, according to the rule that corresponding angles in congruent triangles are equal to each other, and if we define angle PAM, this angle is angle alpha, then angle PAS, this angle will be also equal to alpha because of the fact that those two angles are equal to each other. So we actually found out that angle PAM equals to angle PAS, and they are both equal to alpha according to our definition. Okay? In the next step, we will connect together points A and Q by a straight line. And we will define the touching point between tangent AD to the big circle. This point is point H, and we will join together points Q and H by a straight line. Actually, QH is the radius of this big circle because of the fact that line segment QH starts from the center of this big circle, that is to say from point Q, and ends at point H, that is a point on the circle itself. Therefore, QH is the radius of this big circle, that is to say it equals to 2R. And again, we have rule number 1 that says actually point H is the point of tangency of tangent AG with this big circle. And we have rule number 1 that states that if a radius is drawn to the point of tangency, that is to say point H, then the tangent AB will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? In the next step, we will define the touching point between tangent DC and this big circle as point L. This point, actually point L is the point of tangency of tangent DC with this big circle. We will join points Q and L by a straight line. Line segment QL is the radius of this big circle. Why? Because line segment QL starts from the center of this big circle and ends at point L, that is a point on the circle itself. Therefore, QL is the radius of this big circle, that is to say it equals to 2R. And again, we have the rule number 1 that states that if a radius is drawn to the point of tangency, that is to say point L, then the tangent DC will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. As you can see, the tangent DC is perpendicular to this radius. Okay? And we also know that all the 4 angles inside the square are right angles, therefore this angle equals to 90 degrees. And again, we will repeat on the same process as we did with quadrilateral, the small quadrilateral PEMB. Okay? So we will focus on quadrilateral DLOQ. So in quadrilateral DLOQ, we have 3 right angles, 1, 2, 3. And the sum of 3 right angles is 90 degrees times 3 is 270 degrees. We will define this 4th angle as angle Z. And we have the rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. That is to say, if we focus on quadrilateral QL or DLOQ, the sum of the angles in quadrilateral QL or Q equals to 360 degrees. That is to say, the sum of three angles, that is 270 degrees, plus the size of the fourth angle, that is Z, must be equal in total to 360 degrees according to the rule that I mentioned. We will subtract from this equality 270 degrees, and we will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that angle Z is a right angle, that is to say it equals to 90 degrees. So we actually found out that all four angles inside quadrilateral QL or DLOQ are right angles, they are equal to 90 degrees. And we have a rule that if a quadrilateral has four right angles, it must be at least a rectangle. If not a square, it must be at least a rectangle. So quadrilateral DLOQ must be at least a rectangle and we know that the opposite sides of a rectangle are equal to each other. That is to say, if we relate to quadrilateral DLOQ, that is actually a rectangle, OQ will be equal to DL. OQ equals to DL, but we know that OQ equals to 2R. OQ equals to 2R, and from this equality we will conclude that DL also equals to 2R. DL equals to 2R. Likewise, DO equals to LQ. DO equals to LQ. But we know that LQ equals to 2R. And from this equality we will conclude that DO also equals to 2R. DO equals to 2R. So actually we found out that all sides of quadrilateral rectangle or quadrilateral DLOQ are equal to each other. Therefore, quadrilateral DLOQ is a square. Okay? In the next step, we will find out the size of the segment line OA. We know that the size of side DA is 8 units. It is one of the square ABC sides, and all sides are equal to 8 units, so DA equals to 8 units. So, as you can see from the drawing, OA, line segment OA equals to DA minus DO. OA equals to DA minus DO. Line segment OA equals to DA minus DO minus O. OA equals to DA minus DO, but DA equals to 8 units and OA equals to 2R, so in total we found out that OA equals to 8 minus 2R. We found out that OA equals to 8 minus 2R. I write here that OA equals to 8 minus 2R. Okay. In the next step, we will prove that those two right triangles can go into each other. So we will actually focus on the right triangle, QAH, this right triangle, and the right triangle QAO, this right triangle. I will repeat again. We prove that the right triangle QAH is congruent to the right triangle QAO. So first of all, we know that side AH equals to side AO according to rule number 2. AH equals to AO according to rule number 2. Again, side AH of triangle QAH is equal to side AO of triangle QAO according to rule number 2. I repeat again on rule number 2, we have here the external point A, and from the external point A we have two tangents to this big circle, tangent AH and tangent AO, and according to rule number 2, if from an external point of a circle you draw two tangents to that circle, then the length of those two tangents will be equal to each other, and the length of the first tangent is AH, the length of the second tangent is AO, and according to rule number 2, the lengths of those two tangents are equal to each other, that is to say AH equals to AO. Okay, AH equals to AO according to rule number 2, and we also know that QH equals to QO equals to the radius of this big circle, that is to say equals to 2R. QH equals to QO equals to the radius of the big circle, that is to say to 2R. QH equals to QO equals to 2R, and we also have a common side. QA is a common side, it belongs to both triangles, so QA equals to QA, this side, it is a common side that belongs to both triangles. Again, QA equals to QA is a common side. So we actually proved that all three sides, 1, 2, 3 of the right triangle QAH are correspondingly equal to all the three sides of the right triangle QAH. 1, 2, 3. Okay? Therefore, we proved that the right triangle QAH is congruent to the right triangle QAO according to side rule. I write it down. We actually proved that the right triangle QAH is congruent. I will remind you again that this is the sign of congruent, is congruent to the right triangle QAO according to side rule. And from the fact that those two right triangles congruent to each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles congruent to each other, therefore the two corresponding angles, that is to say those two angles, will be equal to each other. So I'll write it down that angle QAH is equal to angle QAO and angle QAH equals to angle QAO, and if this angle equals to beta, then this angle will be also equal to beta because of the fact that those two angles are equal to each other. Okay, so we actually found out that angle QAH equals to angle QAO, and both angles are equal to beta according to our definition. Okay? Actually, we know that angle DAB is one of the square ABCD angles, therefore it equals to 90 degrees. So actually we can write down that angle QA, angle DAB or BAD, angle DAB is a right angle, it equals to 90 degrees. It's one of the square's angles, it equals to 90 degrees. Angle DAB equals to 90 degrees for one side, but from the other side, angle DAB consists of four small angles, alpha, alpha, and beta, and beta. Therefore, the sum of those four angles must be equal to the size of angle DAB, that is actually 90 degrees. That is to say, 2 alpha plus 2 beta equals to the angle DAB. 2 alpha plus 2 beta equals to angle DAB, and from this equality we will conclude that 2 alpha plus 2 beta equals to 90 degrees. Okay? This will be equation number 1, that 2 alpha plus 2 beta equals to 90 degrees. Here we will divide equation number 1 by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. But if alpha plus beta equals to 45 degrees, then tangents alpha plus beta will be equal to tangents 45 degrees. Very simple. So tangents alpha plus beta equals to tangents 45 degrees. So, or tangents alpha plus beta. Actually, tangents 45 degrees is 1. So we actually found out that tangents alpha plus beta equals to 1. Okay? But we actually have a trigonometric identity for the value of tangent alpha plus beta. The following trigonometric identity is the trigonometric identity for the value of tangent alpha plus beta. Actually, tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay? So according to this trigonometric identity, we can substitute the value of tangent alpha plus beta in this equation number 1 by this expression that equals to tangent alpha plus beta. So we will do it now. So equation number 1 will be instead of tangent alpha plus beta, we write down that this expression that equals to tangent alpha plus beta, it is actually tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta and in equation number 1 tangent alpha plus beta equals to 1, so this expression equals to 1. So we substituted the value of tangent alpha plus beta by this expression that equals to tangent alpha plus beta, and according to equation number 1, tangent alpha plus beta equals to 1. Okay, so in the next step we will find out the values of tangent alpha and tangent beta, and we will substitute tangent alpha and tangent beta in this equation number 1 by the value that we will find for tangent alpha and tangent beta. Okay, so we will focus on the right triangle, triangle APM. So in the right triangle, triangle APM, tangent alpha equals to PM over AM. I repeat again, in the right triangle, triangle APM, tangent alpha equals to PM over AM, tangent alpha equals to PM over AM, but we know that PM equals to R and AM equals to 8 minus R. We have already found out that AM equals to 8 minus R, so in total we got that tangent alpha equals to R over 8 minus R. Tangent alpha equals to R over 8 minus R. In the next step we will focus on the right triangle, triangle AOQ. So in the right triangle, triangle AOQ, tangent beta equals to OQ over OA. I will repeat again, in the right triangle, triangle AOQ, tangent beta equals to OQ over OA. Tangent beta equals to OQ over OA. But we know that OQ equals to 2R and OA equals to 8 minus R, 8 minus 2R, 8 minus 2R. So in total we found out that tangent beta equals to 2r over 8 minus 2r. Okay, so we found out that tangent beta equals to 2r over 8 minus 2r, and we have already found out that tangent alpha equals to r over 8 minus r. So we will actually substitute the values of tangent alpha and tangent beta by those two values for tangent alpha and tangent beta in this equation number 1. So we will do it now. So according to equation number 1, tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta equals to 1. And we have already found out that tangent alpha equals to r over 8 minus r plus tangent beta. We have already found out that tangent beta equals to 2r over 8 minus 2r. And we divide tangent alpha plus tangent beta by 1 minus tangent alpha times tangent beta. Tangent alpha is r over 8 minus r times 2r over 8 minus 2r. And tangent alpha plus beta equals to 1. So again, we substituted tangent alpha and tangent beta in this equation number 1 by the values for tangent alpha and tangent beta that we found by those two values, and we got this equation number 1. So we have here one equation with one variable, that is r. We will take out a common factor for these two expressions, and we will also take out a common factor for 1 in this expression, and we will actually find we get that here a common factor for those two expressions will be 8 minus r times 8 minus 2r. This is the common factor of those two expressions. And here we will have to multiply r by 8 minus 2r in order to get this expression. And we will multiply 2r here by 8 minus r in order to get this expression. And we will divide it here all by 1 minus this expression. We will take out the common factor for 1 in this expression. The common factor will be 8 minus r over 8 minus r. We will substitute 1 by the following expression. 8 minus r over 8 minus r is 1, and we will multiply it by 8 minus 2r over 8 minus 2r. 8 minus 2r over 8 minus 2r is 1. So we actually have here 1 times 1 is still 1. So actually all this expression equals to 1. Then we have to subtract from 1. We subtract from 1. R times 2r is 2r squared. All equals to 1. So actually here we have in the numerator 8 minus r times 8 minus 2r, and we have in the denominator 8 minus r times 8 minus 2r, the same expressions. And we will, when we will divide those two equal expressions one by the other, it will be equal to 1, so it actually will get cancelled. So we will cancel those two expressions. And what is left after we cancel those two expressions, so it is actually, what is left is, in the numerator is r times 8 minus 2r plus 2r times 8 minus r over, in the numerator, this is what we have in the numerator, and in the denominator we will have 8 minus r times 8 minus 2r minus 2r squared. All this expression equals to 1. Okay, so here we will cross multiply this expression, equation number 1, and we will get that r times 8 minus 2r plus 2r times 8 minus r equals to 8 minus r times 8 minus 2r minus 2r squared. All of this equals to 1. So we actually got this expression after we cross multiplied this equation number 1. So here we will open the brackets in both sides of the, in this side of the equation, on both sides of the equation. Actually it equals, it is not 1, but this expression equals to this expression. We will open the brackets in both sides of the equation number 1, and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, 2r times 8 is 16r, 2r times minus r is minus 2r squared, all equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, minus r times minus 2r is plus 2r squared, plus 2r squared, minus 2r squared, plus 2r squared, minus 2r squared equals to 0, so those two expressions will get cancelled, and what left after we cancelled those two expressions is actually here we have 8r plus 16r is 24r, minus 2r squared is minus 4r squared. It equals to 64. Minus 16r minus 8r is minus 24r. So here we will subtract 24r from this equation number 1, and we will get that minus 4r squared equals to 64 minus 48r. We will subtract, we will add 4r squared to this equation, and we will get that 4r squared minus 48r plus 64 equals to 0. We will divide this quadratic equation by 4, and we will get that r squared minus 12r plus 16 equals to 0. So we have here a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. So here a, b, and c are the coefficients of this general quadratic equation, and x is the variable that we are looking for, and we will find out the value of x by using the following equation for x. The following formula: x actually equals to minus b plus minus root of b squared minus 4 times a times c over 2 times a. Okay, so in our specific quadratic equation we have r squared minus 12r plus 16 equals to 0. The coefficients, actually the variable in our quadratic equation is r, so x equals to r, and the coefficients a, b, and c are as follows: a equals to 1, b equals to minus 12, and c equals to 16. So we will put these values of variables a, b, and c inside this equality. So we will find out x equals to r, so r equals to minus b, b equals to minus 12, and minus b is minus 12 is 12, plus minus root of b squared, b equals to minus 12 squared is 144, minus 4 times a is 1, minus 4 times 1 is minus 4, minus 4 times 16 is minus 64, all divided by 2 times a is 1, 2 times 1 is 2. So we got that r equals to 12 plus minus, actually 144 minus 64 is 80 over 2. Okay, and actually r equals to 12 plus minus 80 is 4 times 20, so we write it down over 2. So r equals to 12 plus minus, the root of 4 is 2, and inside the root we left only with 20 over 2. So actually r equals to 12 over 2 is 6, 2 over 2 is 1, and 20 equals to 4 times 5. So inside the root we have 4 times 5. So r equals to 6 plus minus, the root of 4 is 2, and inside the root we left only with 5. So we have here two solutions for the radius of this quadratic equation, for the radius of the small circle. The first solution is that r equals to 6 plus 2 times root 5. That is the first solution for r, and the second solution for r is that r equals to 6 minus 2 times root 5. Okay? But from the drawing you can see that you can see from the drawing that, first of all, we know that one side of the square equals to 8 units. And those two circles are located inside, totally inside the square ABCD. So the radius of this small circle must be less than 8 units because it is totally inside this square. Therefore, and we know that one side of this square equals to 8 units, and this radius must be less than 8 units in order to be totally inside this square. And the answer that the radius is greater than 8 units is not correct answer. Here, r that equals to 6 plus 2 times root 5 is greater than 8, and r must be less than 8 units. Therefore, this solution is not correct solution, and we left only with the solution that the radius, the second root of the, for r, that is r equals to 6 minus 2 times root 5 units, or in terms of numbers, r equals to 1.53 units. Okay, so we actually found out that the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we have square ABCD. One side of square ABCD equals to 8 units. Inside square ABCD, we have two circles. The radius of this big circle equals to 2r, and the radius of this small circle equals to r. And we want to find out the radius of this small circle, or the value of r, or the size of the radius of this small circle. Okay, before we solve the question, I presented to you two new rules. Actually, the first rule Rule number one was that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number one? The meaning of rule number one is that if we have this circle, and we know that the center of this circle is at point O, this point, and we have tangent AB that is tangent to this circle at point M. So point M is the point of tangency. So if the radius of this circle, that is to say OM, is drawn to the point of tangency, that is to say point M, as you can see in this drawing, this radius OM is drawn to the point of tangency, that is to say is drawn to point M. Therefore, the tangent AB is perpendicular to this radius. That is to say, this angle is 90 degrees, and this angle also equals to 90 degrees. So whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to that radius. In our example, this angle is 90 degrees and this angle is 90 degrees. Why? Because the radius is drawn to the point of tendency. Okay, so that is rule number 1. And I also presented to you rule number 2. Rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? The meaning of rule number 2, if we have this circle, the external point of this circle is point P. So why point P is an external point? Because of the fact that point P is not located inside this circle nor on this circle, but is located outside this circle. Therefore, point P is defined as an external point in relation to this circle. It is external point of this circle. So if from an external point P we will draw two tangents to this circle, then the lengths of those two tangents will be equal to each other. So the length of the first tangent, this tangent is PA. The length of this second tangent is PB. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. Okay, so whenever you draw from an external point two tangents to a circle, then the lengths of those two tangents will be equal to each other. That is the meaning of rule number 2. Okay, in the next step, we will define the center of this small circle as point P, and we will define the center of this big circle as point Q. Then we actually the touching point between tangent AB and this small circle is at point M. Actually, point M is the point of tangency of tangent AB, and PM is the radius of this small circle because of the fact that line segment PM starts from the center of this small circle and ends at point M, that is a point on the circle itself. That is, the shape PM is the radius of this small circle, that is to say it equals to R. So we have rule number 1 that states that if the radius is drawn to the point of tangency, that is to say point M, then the tangent AB will be perpendicular to this radius. As you can see, the radius PM is drawn to the point of tangency, that is to say to point M. Therefore, this tangent AB is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. Okay? And the same thing is true here. We have PF or PE is the radius of this small circle, and this radius is drawn to the point of tangency, that is to say is drawn to point E. Therefore the tangent BC is perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. Likewise, we have PS, that is the radius of this small circle, and the radius PS is drawn to the point of tangency, that is to say is drawn to point S. Therefore the tangent AG is perpendicular to this radius, that is to say this angle is 90 degrees and this angle also equals to 90 degrees. Likewise, we have here this radius that is drawn to the point of tangency, that is to say point O. Therefore this angle is 90 degrees and this angle is also 90 degrees. Okay, in the next step we focused on this quadrilateral PEMB. Quadrilateral PEMB has 3 right angles, 1, 2, and 3. The sum of those 3 right angles is 270 degrees. So we define this angle as angle Z, and we have the rule that the sum of the angles in any quadrilateral equals to 360 degrees. That is to say, the sum of the three angles, that is 270 degrees, plus the size of the fourth angle, that is z, must be equal to 360 degrees according to the rule that I mentioned. We subtracted 270 degrees from this equality and we got that angle z equals to 360 degrees minus 270 degrees is 90 degrees. So this angle is a right angle, it equals to 90 degrees. So as you can see from the drawing, quadrilateral PEMB has 4 right angles. And any quadrilateral that has 4 right angles, it must be at least a rectangle. So quadrilateral PEMB is at least a rectangle. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, PE equals to MB. Those two opposite sides in rectangle PE and MB are equal to each other. PE equals to MB. But PE equals to MB, but we know that PE equals to R. As you can see, from the drawing, PE equals to R. So from this equality, PE equals to R. So from this equality, we will conclude that MB also equals to R. MB equals to R. Likewise, we note that the two opposite sides in rectangle PE and B are also equal to each other. That is to say, PM equals to EB. PM equals to EB. But we know that PM equals to R. PM equals to R. So from this equality, we will conclude that EB also equals to R. EB also equals to R. So we actually found out that in quadrilateral PE and B we have 4 equal sides. All of its sides are equal to R, and it has also 4 right angles. Therefore, quadrilateral PE and B is a square. Okay, then we actually found out the size of AM or line segment AM. What is the size of AM? As you can see from the drawing, the size of AM is actually AB minus MB. Okay, AM equals to AB minus MB. What is this? The value of AB? AB equals to 8 units. What is the value of MB? MB equals to R. Okay, so AB equals to 8, MB equals to R. So in total we found that AM equals to 8 minus R. So we wrote here that AM equals to 8 minus R. Then we actually proved that the right triangle APM is congruent to the right triangle APS. Why? Because AM equals to AS according to rule number 2, because we have here external point A, and from external point A we drew 2 tangents to this small circle, tangent AM and tangent AS. And according to rule number 2, whenever you draw 2 tangents from an external point of a circle, whenever you do 2 tangents to that circle, they are equal to each other in their lengths. That is to say, AM equals to AS according to rule number 2. And we also know that PM equals to PS equals to the radius of this circle, and AP is a common side, it belongs to both triangles, so AP equals to AP. So we found out that triangle APM can go into triangle APS according to side rule. And from the fact that those 2 triangles can go into each other, we will conclude that those 2 angles are equal to each other. So if this angle is alpha, this angle also equals to alpha. Okay? Then we actually did the same process as we did in quadrilateral PEMB. We did the same process in quadrilateral DLOQ. quadrilateral DLOQ has 3 right angles. The sum of those 3 right angles, 1, 2, 3, is 270 degrees, and according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees, this angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral DLOQ to 360 degrees. So this is a right angle. So in quadrilateral DLOQ we have 4 right angles, therefore it is a rectangle. And the opposite sides in the rectangle are equal to each other. So this side OQ equals to DL, but we know that OQ equals to 2R, therefore DL also equals to 2R. And QL also equals to OD, but QL equals to 2R, therefore DO also will be equal to 2R. So quadrilateral DLOQ is a square, and we found out the value of AO. AO actually equals to DA minus DO. DA is 8 units and DO is 2R. In total we found out that AO equals to 8 minus 2R. Okay? Then we proved that those two right triangles can go into each other according to side rule. Therefore, if this angle is better, this angle also better, and this angle is one of the squares angles, angle DAB, therefore equals to 90 degrees, because all the angles in a square are right angles. From one side it equals angle DAB equals to 90 degrees, from the other side it equals to 2 alpha plus 2 beta. So in total we will get that DAB equals to 90 degrees and DAB also equals to 2 alpha plus 2 beta. So from this equality we will get that 2 alpha plus 2 beta equals to 90 degrees. We will divide this equality by 2 and we will get that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Tangent 45 degrees is 1. So we got equation number 1 that says that tangent alpha plus beta equals to 1. And we have a trigonometric identity from tangent alpha plus beta equals to this expression. So we substitute the tangent alpha plus beta in equation number 1 by this expression that equals to tangent alpha plus beta. Okay, and then we found out that here tangent alpha equals to R over 8 minus R, and from this right triangle we found out that tangent beta equals to 2R over 8 minus 2R. So we found out the values of tangent alpha and tangent beta, and we substitute the tangent alpha and tangent beta in equation number 1 by the values that we found out, and we got this equation. We solved this equation. We got 2 answers. The first answer is that the radius of the small circle equals to R6 plus 2 times root 5, or the radius of the small circle equals to 6 minus 2 times root 5, but the radius of this small circle must be less than 8 units because the size of the square equals to 8 units and the circle is located totally inside the square. Therefore, the radius must be less than 8 units. So this possibility is not correct, and we left only with the answer that the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, so repeat again, the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 0.53 units. Okay, thank you very much.